Good day everyone, welcome to this video. In this video I'm going to show you how to code a capacitive touch sensor using a PIC18 microcontroller using only the ADC. And there's another method to do this, to do the capacitive touch sensor, which is the CTMU using the charge time measurement unit, but I'm not going to show you that in this video because I actually tried it and I found it to be quite unreliable, and it works sometimes and other times it doesn't, so it's not reliable enough to make a video about. Essentially, it's very buggy and it triggers itself sometimes, so I will not be doing a video on that anyway. So but this particular video I'm going to show you how to do the capacitive touch sensor using only the ADC. And there's actually an application note about this, which is the EN1298 application note by Microchip, and it essentially explains how to make a capacitive touch sensor using the PIC microcontroller, just using the ADC and the normal code logic of the code. And essentially what you're doing is you're discharging and charging the capacitor, and you're doing this constantly. And once you touch it, your hands, whatever you touch the pad with, acts like a huge burden resistor, and the capacitor does not charge up to its nominal value anymore because you're discharging it essentially. And it won't okay, let's say the capacitor usually charges up to 5 volts. When you touch it, it will not charge up to 5 volts anymore. It should charge up to about 4 volts, 4.5 volts, and the ADC basically senses this as a touch, because there's a resistor, which is yourself, acting as like taking up that charge essentially. So yeah, so that's essentially what this code does. And it's also important to note that in this application note, you're required to use 2 pins for the capacitive touch sensor. But in this example I'm going to show you, I only used 1 pin. Let me just show you the schematic quickly. So this is the schematic, and of the sensor. Yeah, so the metal touchpad here, you could use a coin, I guess, a coin or like a foil or something like that. But I just used a piece of wire in this particular example. I just used a wire. You could use a coin if you really want to. Guess it looks nice and professional, but I used a piece of wire and it worked just fine. And with regards to this resistor, you don't have to include this resistor here, but I found that when I included it, I got a better range. So let's say usually the value I read from the ADC is about 250 when I sense a touch, 240, 250, 240 to 250. Usually without this resistor, that's what I get. But with this resistor, it goes down to about 220. And a difference, 220, a difference of 35 between 220 and the max value of 255. That's a bigger difference than say 15 if the value was what, 240. So what I'm trying to say is you get you're able to sense a touch better by adding this resistor here, and this obviously is power. It's almost like a pull-up resistor, but you don't have to add it, add the resistor. But once you add the resistor, it works better from my experience. And this is the analog pin, and this particular resistor, try not to go too high. Try to limit it to about 1 mega ohm, and the minimum should be about 600 kilo ohms, no lower than that. Don't put something like I don't know, 10k ohm or 1k ohm. Yeah, it will do absolutely nothing, so don't do that. Anyway, so this is basically the hardware required for the cap touch sensor, and Yeah, that's it. And also for this example, I connected an LED over here to show that I actually sensed the touch. I'm gonna show a video at the end of the actual thing, not on Proteus because I can't really simulate a cap touch in Proteus. Okay. Yeah, so I'm just hop over to the code now. Let's just close that. So the application note, I'm still here. Yes. Okay. So with regards to the application note, I'm gonna link that in the description, the application note. You could go take a look. I'm not gonna read through it in this video. It's just gonna make it longer than it has to be, honestly. So let's just get to the code. Yeah, so this is the code. The code begins as normal. The configuration bits are here. You have the configuration bits. It's a little slow. Just have patience. Yeah, up to the configuration bit you have the C block, and up to the C block I'm gonna explain this threshold value, cap threshold just now. And then yeah, the code begins as normal, and then you have the initialization, you initialize the oscillator of the PIC microcontroller. The speed is 4 megahertz, and the ADC, initialize the ADC and initialize the port. And in essence, the port initialization here is just for port RD1, and that's the LED to indicate that a touch has been sensed, essentially. And ADC initialization, I'm going to go through that now. I just want to do a quick overview of the code before I dive deeper into it. So first off, we call the main cap routine, and essentially in this routine, that's where the cap touch, the main thing happens. Actually, the charging and discharging happens. Okay. And then after that, excuse me, and then after that we test the cap range register. So what happens in the cap routine is essentially if a touch is sensed, the cap range register is going to be set, and by set, when you set a register, the value of the register becomes 255, and when you clear it, it's going to be 0. So what the cap routine does, what this particular function does, is in that function, if a touch is sensed, it's going to make the cap range register 255, and if it's not sensed, it's going to make the cap range register, this register, is 0. So basically, to turn on the LED after the cap routine, all we have to do is just test the cap range register, which is exactly what's done here. So you test this line tests the cap range register, and if it's a 0, it's going to skip the next line. What this line does is it's a tests function skip if 0. So once it tests that and it's 0, it's going to skip the next line, which is this, and it's going to skip that line and turn off the LED if the LED was on. So it's going to turn it off and basically loop, and it will carry on checking the cap routine. It will keep on checking if the touch has been detected, because remember, you don't want to, usually when you have a cap touch routine, you have the cap touch to essentially start your code with. And if the touch, if you're not able to sense the touch, then you don't want to carry on with the rest of your code. But if the touch is indeed sensed, then you want to carry on with it. So that's why essentially it's going to loop around until the touch has been sensed over here, and the LED will stay off. But if a touch has been sensed, then the cap range register is not going to be 0, it's going to be 255, and then the next line will not be skipped. And then it's going to jump over to this label over here, which is the main L1 label. Let's go there. Yeah, this is the main L1 label, and what that does is it turns on the LED to show that a touch has been sensed. It turns on that LED, and then it loops and loops again. So yeah, that essentially is the code. So now I'm just gonna dive deeper. First off, I'm gonna go to the ADC initialization. Just a function. I'm just gonna click on that. Okay, that's not working. Okay, yeah, it's there. And then this is the ADC initialization. So for the ADC, there are three things you need to note. The ADC initializations is actually one of the easiest modules to initialize in the PIC18 microcontroller. So the only things you have to worry about is essentially choosing the pin that you want to scan, which is what these 5 lines do. You use that to scan the pin. I'm not going to use the datasheet to initialize this because the ADC initialization is actually very straightforward, as I'm going to show you now. And then after that, the registers you have to worry about to initialize the ADC are 3 registers: the ADCON 0, ADCON 1, and ADCON 2 register. And the ADCON 0 register is essentially to turn the ADC on and to select the pin to be sampled, and to select the sampling pin. And this particular microcontroller, I think it has about 11 pins that you could sample from. I'm not so sure about that, but I think it has quite a few pins you could sample from. Anyway, you choose them using these bits of the ADCON 0 register, and afterwards you could you have to set or clear the go bit to begin a conversion, but we're not starting a conversion now, so the bit will remain cleared in initialization. And just before I carry on, yeah, I set this up to use the AN1 pin of the microcontroller. That's why I set up as such, these 5 bits. And next, after you clear the go, because we're not starting conversion, but you have to enable the ADC module, and you do that by setting the ADON bit of the ADCON 0 register. And after that's done, you move into the ADCON 1 register, and essentially in the ADCON 1 register, what you're doing is you're setting up the reference for the analog to digital converter, because the particular the ADC module in the PIC microcontroller allows, I think, negative and positive and negative references, but we're not going to be using a negative voltage reference. We're going to use the 0. 0 is going to be the lower limit of the ADC, and VDD is going to be the upper limit. VDD being 5 volts essentially. And so to set that up, you just clear the ADCON 1 register, and then after that the ADCON 2 register, and this essentially is the register where you set up the timing requirements for the ADC. And over here in the ADC, first off, you have to left justify, and that has to do with regards to the results, how you want to view your results. I'm gonna go there just now to the data sheet. Mind the data sheet, yes, on the data sheet. So I'm just gonna go down to the ADC section, analog to digital converter, and essentially the ADC, it's a 10-bit analog to digital converter that's in the PIC microcontroller, but remember, in assembly it's much easier to work with 8 bits than it is with 10 bits. So essentially what left and right justification does is this. So if you left justify, then most of your bits are going to be in the ADRESH register. The 8 bits are going to be in the ADRESH register as such. So wait, yeah, because it's left justified. If it's left justified, most of your results are going to be in the ADRESH register, and only the least 2 bits are going to be in the ADRESL register. And if it's right justified, most of your bits are going to be in the ADRESL register, and only 2 upper bits are going to be the ADRESH register. And one thing you have to take note of is if, for instance, you have you're trying to sense, what you're trying to sense has a lot of noise in it. Then the 2 least significant bits are going to be pretty much useless. So you want to left justify in that scenario. Let's say, for instance, you have a color sensor. You're going to have some noise in it, so you're going to want to left justify in that scenario. But let's say you have something like something that's very sensitive, for example, like okay, this is a bad example, but like a cap touch, for instance. Let's say you wanted to sense a cap touch, then you're going to want to right justify. You're going to want to right justify because most of the values you're going to be getting are going to be small, pretty small, so you're not going to require 10 bits. You probably require only 8 bits, so in total. And that's why you're going to want to right justify in that scenario. But that's essentially what left justification and right justification means. I hope I explained that properly. I'm pretty much convinced I didn't. But when you right justify, most of the bits are going to be the ADRESL. If you left justify, most of your readings are going to be in the ADRESH. So that's that. Let me just go back to the code now. MPLAB. There we go. Yes, and that's that. And the next one is for the ATCON. The next one deals with the acquisition time. Essentially, what the acquisition time is, when you want to sample using the analog to digital converter, what happens is the capacitor inside of the ADC is connected. It's connected for a certain time period, and that essentially is the acquisition time. So if the capacitor is connected longer, you're gonna have a more accurate reading because it will be charged up for longer with whatever you're trying to sense. And yeah, so that in essence is the acquisition time. That's what it concerns. And these 3 bits, ACQT2, ACQT1, and ACQT0, are what you initialize to set up the acquisition time. In this case, I used 8 TAD. You could use 4 TAD or 16. It doesn't really matter, honestly. You could use whatever you want in this case. That's the acquisition time. And the last one is the ADCS, is the clock select bits. ADCS2, oh no, this is actually supposed to be 1 and 0. Okay, those are actually supposed to be, so it's ADCS2, ADCS1, and ADCS0. So that sets up your clock speed to be 600 kilohertz, which is the nominal clock speed of the ADC. You could set it up to be much faster than that, but I find that this works fine for me most of the time. And that in essence is how you set up the ADC. I think I should show you quickly what it looks like on the datasheet before we carry on. Okay. So these are the registers. Let me just go there. Let's go there. ADCON 0. So as you can see here, these are what you use to select the sampling. The sampling. Let me just go there. Okay. I'm just trying to get, yes. So at con 0, so as you can see here, this is what you use to set up the pin that you want to sample, the ADC pin that you want to sample. So the first bit is bit 7 is unimplemented, and bit 6 to bit 2 are what you use to set up the pin that you want to sample from, N0, N1, etc. There's actually 27 of them, which is, I had no idea there were 27 of them. Anyway, so on the go bit, obviously to start a conversion process, and bit 0 is the ADON bit to enable the ADC, and the ADCON 1, like I said, essentially we just clear this register. It works all the time. Here, as you can see, this 2 bits, 0 0, bit 3 and bit 2, you clear both of them to use the VDD as the positive reference for the ADC, and the last 2 bits you clear them as well to use to ground the VSS as the negative reference of the ADC, VREF minus of the ADC. So as you can see, we just literally just clear it. And also here in the last one, at con 2, the bit 7, you use that to left justify and right justified, as I badly explained earlier on. And then bit 6 is unimplemented, is read as 0, and then from bit 5 to bit 3 is literally this. So you could choose that. That essentially is the acquisition time, holding time for the capacitor, how long the capacitor is essentially going to get charged. And the ADCS, as you can see, is the clock speed for your ADC. And I chose FRC. I chose this bottom one here, 600 kilohertz nominal, which means ADCS2, ADCS1, and ADCS0 are all set, which I did in code. And that in essence is ADC, honestly guys. ADC is the least, it's the least complicated module. So straightforward. Honestly, you could literally get away with not reading the datasheet and code ADC just fine. Okay, let's get back to the code. Just click that and we're back with the code. And that in essence is the initialization of the ADC. And next is, yes, I want to show you first off how an ADC conversion is done. And to do an ADC conversion in essence is, just double click, yes. So to start an ADC conversion, you have to set the go bit of the ADCON 0 register, set the go bit, and that begins conversion. And then once conversion has ended, this particular bit, the go bit, is going to be cleared. So in essence, to do an ADC conversion routine, you have to pull the go bit of the ADCON 0 register, and if the bit is cleared, you know conversion has been completed. And by the way, in this particular example, I left justified because the value always goes to 255 by default. So basically it means most of the readings we're concerned with are in the ADRESH register. If that was a bit confusing, don't worry about it. Honestly, just know it works better. This code works better with left justification. Yeah, this should be fine. So yeah, so the go bit is going to be cleared once ADC conversion has been completed. And once the ADC conversion has been completed, we'll move the ADRESH register, this value, the whatever we read essentially comes into this register, and it's moved into this particular variable here, ADC result H. This is a variable that was created in this code, and the ADRESL, obviously, and this value is actually not really needed in this code, but you know, it's there. So that's that. So that's the ADC conversion routine. Let me just go over it one more time. First off, you set the bit to begin conversion, the go bit to begin conversion, and then right afterwards you poll it to check if it's been cleared. If it's been cleared, then conversion is ended. If it's not been cleared, then you essentially, it's not going to skip the next line, it's just going to keep polling. It's going to keep jumping to this line, to the BTF, skip if cleared line. But once it's cleared, conversion has been ended, and it's going to skip the next line, which is BRA ADC poll, and store the values that have been read into these registers, the ADC result H and the ADC result L register. So that's ADC conversion. And then if we go back to main, now we can go into the main cap routine. And yeah, so this is the main cap routine. And if you look in the main cap routine, this is what happens. So first you call the cap touch routine. I know this doesn't make a lot of sense because I said this is the routine where it happens, but actually it's in two levels. So this is the first level, the main cap routine. So in the main cap routine, you call the cap touch routine. This is where it really happens. I promise you, it actually happens in this function. And then there's a 1 second delay to avoid false detection, because what happens sometimes once you start the code up, there's usually the capacitors, for some reason, I guess they're charged up by default or something. Honestly I don't know, because they trigger themselves at first. But so it's advisable to check them twice, to sense if there's been a touch. So the way you check them twice is essentially you check it once, and then you get a delay, you implement a delay, a 1 second delay, and then you check them again, and to sample twice to avoid false triggers essentially. And then next you check the threshold. So this particular threshold, how we sense there's been a cap touch is if if the value of the ADC result H register, which is what we just sensed from the ADC, if that value is below this particular threshold, there's been a touch. So how we do that is literally we move this cap threshold value into the working register, and then we compare with the actual results that we read from the analog, from the ADC module. And if it was less, if the cap threshold value is less than this value here, then we skip the next line. Which means there was a touch. We skip the next line and we set to this register. We make 255 to be in the cap range register essentially, which that's what this line means. Set F cap range, and we exit the routine. But if it's not less, if the cap threshold value is not less than this particular value, let's say it's higher, then the next line is going to be skipped. It's not going to be skipped. It's actually going to execute this line, and it's going to go here, over here. And as you can see, that cap range value is going to be cleared. As you can see, the comment says here, clear cap range if touch is not detected. So if this value is cleared, touch was not detected, and we're going to exit the routine. And that's that. And that in essence is the main cap routine. So you go there, we check the cap touch, we check it, which essentially means we're sampling the ADC. That's what we're doing in the cap touch routine, essentially what we're doing. And then afterwards we're charging and discharging, and then sampling the ADC. We're discharging, charging, and sampling the ADC inside this routine, which I'll show you just now. And then we'll move the literal. This threshold value is a value you have to set up at the beginning over here. You can see here the cap threshold. I set it up here to be 240, which is quite high, but it works just fine, I promise. And anyway, after that, the cap threshold, So we compare that with the ADC results H that we got from the cap touch routine. We compare it with that, and then if it's less, if the ADC result is less than the cap threshold value, a cap touch, a touch has been sensed. It means we have indeed touched the panel, right? And which means this guy is going to be set. There's going to be a value of 255 in the cap rate register, and the routine is going to be exited. And then if a touch was not sensed, the next line won't be skipped. It will execute this line and go down here and clear the cap rate register, and that's it. In essence, is the main cap routine, and this is the cap touch routine over here. This is the cap touch routine. So this is the routine where the action happens, like I promised. Where the actual cap touch routine action happens, and which in essence is this: you discharge and then you charge. So first up, there's a 1 millisecond delay, and then next, the AN1 pin is made to be a digital output, and then it's made to be a digital output. These two lines are essentially to disable analog functionality, the first two lines, and this line, let me just put a space there, and these two lines to make it to be a digital output and to discharge the capacitor here, bit clear function port A1, and this discharges the capacitor. And then now we'll wait for another 1 millisecond, and then after the 1 millisecond we charge the capacitor. How do we charge the capacitor? We just literally set the pin, and once you set the pin, the capacitor just starts to charge, and then you wait for 5 microseconds, and then after that you initialize the pin as a digital input, and after it's initialized as digital input, we'll wait another 5 microseconds, and then now we do the analog conversion, the ADC conversion there. First off, we initialize the pin as an analog input now, and then we select a channel, which is AN1, using this 5 lines to select the channel, and then we perform a conversion right after that. And that in essence is the cap touch routine. So let me just explain it again. So first off, we start with the 1 millisecond delay, then we initialize the pin as an output, we make the pin an output, we discharge the capacitor, the ADC capacitor, by clearing the pin, and then we'll have a delay, then we charge the capacitor by setting the pin. Now to charge the capacitor, we'll wait again for a short period of time. We initialize as an input. We initialize the pin as an input, then we'll wait again for another 5 microseconds, and then after that we initialize the pin as an analog input, AN1, and then we'll sample the pin, and then we'll perform the conversion. And then in essence is cap touch. It's a bit weird. It's weird because to charge and to discharge a capacitor, you have to make it an output and an input, because remember, we have to make it an analog input to actually sense the pin, but to actually discharge it, it cannot remain an input. It has to be an output for us to charge and discharge the capacitor. But anyway, in this particular example, you don't have to worry too much about charging it using the code. It's going to be charged permanently using the resistor from the schematic I showed earlier on. But anyway, this is the routine that I managed to get to work constantly. You could play with the delays. I'm guessing this delay here doesn't have to be 1 millisecond. It could be 125 microseconds or 250 microseconds. You could play around with that. It's not a problem. But anyway, and lastly, before I show you the video of the working system, you have to calibrate. So how do you calibrate? You essentially put a, what is it? You put a breakpoint over here, and then you have to go down to, you have to debug essentially to find out the actual value that's gonna be in the ADC register, the value that's gonna actually be read by the ADC when you touch the panel, the capacitive panel. So that's important to know what that value is. For me, that particular value is around 215, 220, but for you it might be different. It might be lower, it might be higher, but you have to check that so you can adjust your threshold accordingly. But for most people it should be below 240, so this should work for most people, but it's important to just calibrate just to make sure, so you don't, take forever, spend the whole day on something that could be fixed with calibration. So let's just go to the watch window, and yeah, I'm just gonna bring out the watches. Okay, and as well here in the watch window, usually by default MPLAB does not allow you to have specialized variable names over here to pop up while you're debugging. So to fix that, you have to go over here into settings. Under settings, it's taking a while to load. Okay, and on the settings over there, you go to MP. When the window opens, you go to MPASM, build in absolute mode, and then you apply, and okay. Also, i.e. variables you created in the C block. And yeah, and as for the delays, I'm not gonna get into that in this video. I think it deserves a video of its own. Those delays especially, there's a whole formula for that. I'll probably put a link for that in the description for another video just explaining these delays. It deserves a video of its own. Anyway, let me just get back to it. The main function, and let me just save that and debug. And essentially what's gonna happen, it's gonna stop on that line, it's gonna hit a breakpoint on that line, and I'm just gonna try to step through the code to show you the actual value that's been read when I touch it versus when I don't touch it, when I don't touch the pad or the wire in this case, which is just a piece of wire in this case. I know I'm still here. It's taking forever, but it's important, so I'm just gonna have to wait. You could just fast forward this part, honestly. Okay. So launching. Okay. And there we go. It's gonna run and halt. Target is halted there. If I go to the watch window, under ADC, I'm not so sure if you guys can see that. Okay, I'm not sure I can zoom into that, unfortunately. Okay, I can't zoom into the area below. I hope you guys can see there's a value of 255 there under ADC result H. So if I run through the code again, it's still okay. Wait, there's a the value remains 255. If I run through it again, 255, still 255. But if I touch it, you'll notice that that value changes. As you can see, it's 234 now, 237, 235. Okay. As you can see that value is actually below 240. And 255. I'm not touching it anymore, that's why it's 255 over there. Maybe you see I touch it again. Well, you guys cannot see if I touch it. I'm being ridiculous. But just trust me on this, I'm touching it right now. You can see the value is lower now. And I'm not going to touch it now. And 255, touching it again, lower, 223. It's actually a lot lower now, which is good. Okay, and now that's bang on 240. Anyway, that essentially is cap touch routine. You can go through the code a couple of times to make a lot more sense. And as for this part, like I said, for the cap touch, usually when you're using a cap touch, you're using it to start up your code, and to start up your code, essentially you're gonna have to put the rest of your code under the main L1 label. So the rest of your code is gonna go here, and that essentially is it. But the rest of the code in this scenario is literally turning on an LED. But in your other applications it will be a lot more things, so you would want to put that underneath this label right here. And if the rest of your code is saying the interrupt routine, right, then essentially what you do after this main L1 is you'd enable your interrupts. You would enable them, and this go to main, you don't want to go back. You're just gonna put a $sign there. So in essence, you're gonna type your interrupt, you're gonna enable them, and you're just gonna go to $sign, and the code is just gonna be stuck there. But when you do interrupt, it's gonna interrupt your code, etc., and it's all gonna be fine and dandy. So, but in this case, it's just gonna be go to main. I think I'm just put that at the bottom. Go to $sign. I'm just gonna comment that out. So if the rest of your code has interrupts, then you want to use the $sign. If not, you're just gonna use go to main in this, if the rest of your code is in this particular fashion. Actually, before I forget, if the rest of your code is gonna be in the main function, you're actually gonna use main L1, because you don't want to continue checking touch, right? Because you just want to check it once and then carry on. So you would actually go to main L1, not main, right? But in this particular example, we want to keep turning on and off the LED based on the touch, so we want to keep checking the capacitive touch, so that's why it goes to main. So in your other applications, comment out go to main, use this particular one, and have fun. Hopefully this coding the capacitive touch sensor. And if you have serious questions, you can just ask them. I'll try to respond to them, because cap touch is tricky. Sometimes it's difficult to get it right, but as long as your cap threshold value is high enough, it should be fine. 240 should be good enough, believe me, should be good enough. But always check like I just did. Always make sure you check constantly to just see where it's at. As such, you see 255 now. A touch, a sense touch is 218. Just make sure you check that, because sometimes your baseline value might not be 255, it might be something else. So you want to make sure you have a good range of your touch and a good value for when it's touched and when it's not touched. Okay, and then everything else should be fine. Alright guys, so that's it. I'm gonna queue in the video now for all this time, and good luck coding the cap touch.